from biological immune systems. Um, and I want to be precise about the analogy because it's not the metaphorical. So here, the SSM, which is a spike stream monitor, is our innate immune response. So it computes real-time rolling statistics on four metrics: instantaneous spike rate, inter-spike interval distribution measured via KL divergence from a learned baseline, and a spatial density mapping across the neurons. So here, with the STDP integrity validator, which is SIV, is our adaptive immune component. So it takes periodic weight snapshots and performs trajectory analysis. So this is critical for distinguishing legitimate STDP learning, which does change weights. So from adversarial manipulations, right? So that the trajectory analysis looks at the direction, magnitude, and also the coherence of weight changes relative to this input signal. So the legitimate learning provides correlated gradual shifts. So the attacks produce abrupt and uncorrelated jumps here. So coming to the next slide here, let me walk through the STARTS algorithm steps, right? So the STARTS stands for spike timing anomaly recognition through temporal statistics. So in the step one, we analyze the temporal buffer B that maintains a sliding window of recent spikes and an anomaly accumulator omega set to 0. So for each income spike, we examine all spikes, right? So which is like where the absolute timing difference delta is less than the STDP window parameter. And in the step three, like each spike pair, we compute the expected probability. And here in the step four, if P fails below our threshold P, then that means like the timing relationship is surprisingly unlikely. So we accumulate the log inverse probability as a surprise score. And in the step five, when the accumulated surprise omega exceed our detection threshold theta, we trigger an alert with a confidence score computed as a sigmoid of the excess surprise. So, and the step six is the buffer maintenance and the accumulator reset on alert dispatch. So these properties make starts effective. So the first is bio-inspired. The surprise accumulation mirrors how biological immune systems detect foreign patterns. So the second is the adaptive baseline, means it evolves with the system's normal behavior, reducing false positives as the model learns. So the third one is the computational complexity, which is O of n times k per spike. So where k is the buffer window size, this is critical for achieving the 3ms response time.
1 minute, please.
Oh, so this is this slide covers the experimental methodology, and so these all are the results and the detection results where the central empirical contribution is. And here, if you see, the response time is arguably as important as the detection rate for neuromorphic security because STDP attacks cause permanent weight changes within milliseconds. And now, so in this slide, we show the comparative analysis of why the domain specific detection matters. And so finally, like what we conclude here is as neuromorphic computing scales to cloud infrastructure, we need security frameworks that defend the learning mechanisms itself, not just the data flowing through it. So the NeuroShield establishes that foundation. And finally, sorry to walk through so fast, but thank you for your attention, and I'm happy to take any questions. If you are interested in the full detection results or response time breakdowns, I have those in appendix slides. You can also reach out to me at nv262@cornell.edu for follow-up questions or discussions or any collaboration opportunities.
Thank you very much for your presentation and for finishing in time. I don't know if anybody wants to make some questions or some comments. I will make just a brief question, an overview question, so that so what's the state of this type of neuromorphic systems applied in reality? Have they already been deployed? Are they a reality now in cloud-based services? Can you just give us an overview of how far has this reached?
Yeah, so there are like a few researchers that were already there, as I have mentioned. So those didn't significantly explore on the multi-cloud. So that's the problem that we were mainly tackling here. And also like with the current, given the ratio of the LLMs and also the AI agents here, so there is a huge chance of the neurospike attacks that might be happening. So we don't have the evidence properly of like the poisoning of those, but like we thought in the direction of the simulation and we executed this.
Well, thank you very much for clarifying this. It looks like a very interesting work and probably lots of new contributions for the future, apparently. Well, thank you very
Thank you so
much.
much.
Thank you. We'll pass then now to the second presentation. It's paper 193, evaluating the vulnerability of deep fake image detection models to adversarial manipulations. The authors are Prakriti Shakia, Katya Makhtian, and Rashida Hassan. We have Prakriti here. Yes. Thank you. So again, I will ask you if you can keep the 10 minutes limit, please. I will warn you a little bit before the around the 9 minutes length, just so that you know. Yes, for a 1 minute. And please, you may start.
Okay, thank you, Daniel. Hello, good afternoon, everyone. My name is Prakriti Shakya from California State University, Northridge. Today, I'll be presenting our work titled Evaluating the Vulnerability of Deepfake Image Detection Models to Adversarial Manipulation. Well, deepfake detection models have recently achieved near perfect accuracy under benchmark datasets. But however, when it comes to adversary manipulations or distribution shift, the model seems to be very vulnerable. And to show this, let's begin with the illusion of the perfection. As I said, within the benchmark, the detectors perform very well, leading many to believe that the problem is largely solved. But there is a hidden assumption that the training and the testing, both the data sets are coming from the same distribution, which in the real world may not be the true. So to see how when the attackers are like actively trying to evade the models, so to see how it performs when there is an attack, we introduce the adversarial trait model. In this setting, the adversary when they try to attempt to manipulate the input data, and which produces false or predicts incorrect output to the detectors. To simulate this behavior, we generate adversarial examples using projected gradient descent, or PGD. PGD is an iterative gradient-based attack which manipulates the inputs in such a way that it maximizes models classification while keeping the perturbation very low. Using this attack framework, we introduced three research questions: that how vulnerable are these detectors under PCD attack, and does training the models with adversarial training increase their robustness, and does robustness transfer across different data sets? Before jumping to the results, this is how the models reacted when there was attack and without the attack. Without the attack, the detectors were able to predict it correctly with near perfect accuracy, as we saw in the first baseline experiment. And when there was attack or the perturbation added, the predictions were unreliable. With the further results, we show that the high benchmark accuracy does not guarantee real-world robustness. To quantify the vulnerability, we stress test several architectures across different data sets. We use both the families CNN and transformer based, where using models like ResNet 18, which is residual connection based, EfficientNet, MobileNet, ConvexNet, ConvexNet, NextTiny, and Bison transformer across Celebrate, real versus fake data set, and face forensic plus plus. We're using the PCT to create the adversarial attack. So this is one of the experiments where we train our model on the clean data set and tested an attack data set. When we did so, the performance dropped dramatically to 50% of accuracy and 0.5 precision, while the recall stayed at 1, which means the model is classifying almost everything as the same class. This one is only when like the models are not introduced to attack once. So what if we train the model which already knows the attack? When we did so, the training and the testing data set were matched. The performance returned to near perfect level again, like with above 99% of the accuracy. But we're saying this as a bandit because this is yet not generalized because the model still is exposed to its distribution. So to evaluate its generalization, we train our model on different attack face forensic plus plus, which is using deepfake or face swap, and tested on the celeb data set, which is using PCD attack. While doing so, despite the models were exposed to the adversarial training, the model failed to generalize, leaving us to the finding that the robustness is dataset specific. And adversarial training is still a memorization technique and not a universal cure. Now jumping to the three questions that we were trying to investigate. How vulnerable are detectors under PCD attack? With the result, we see that the performance dropped to the chances with the recall as 1 and precision to 50%, which we stated as a semantic blindness. But the interesting thing is that when we were testing the model with the real versus fake data sets, their performances were 95% to 95% accuracy, which states that the models are not only the robustness is not only model dependent but also strongly dataset dependent. The model were able to learn the strong features in real versus when it was trained with real versus fake data sets, which were not disrupted by adversarial attack. Then we expose our models to the adversarial attack. Doing so, the models were able to gain the good performance, but the robustness is only when the train and test attack matches. So, like, does the robustness generalized? When we did our cross data set, we see that the model, which was efficiently working so good, also failed to generalize when the attacks were changed. The vulnerability gap that we're talking about is the gap between the baseline, the benchmark data sets that it performed well on, and versus the reality data sets that we're looking at. The accuracies, they drop like to chances. So when the detection is a coin flip, it's not only just the impact, but it's not just academic, it's the matter of its impact. So these are the few points when vulnerable deepfake detections create. Identity fraud, like when authenticators cannot distinguish real users from deepfake. Second, misinformation. Automated campaigns bypass security unchecked. Third, digital forensic. Evidence reliability is compromised. Last and important one, the PCD is imperceptible to human eyes. So even if you want to do it manually, it's not possible. Last, the main verdict that the benchmark is misleading. The high in distribution accuracy is a false proxy for real world reliability, and we see that the detectors are highly fragile when it comes to adversarial manipulation and distribution shifts. And transferability is still a problem. Adversarial training is not a cure, it's just a memorization still. Concluding with that, the current detectors are not yet ready for the hostile environment, and adversarial training helps locally but fails globally. Which we need for that we need robustness aware evaluation protocols and development of adaptive defense that generalizes across manipulation types. Thank you. I'll be happy to take any question.
Thank you very much for your presentation. Before time. Yes, before time. So anyone wants to make some question or comment regarding this work that was presented? I have a comment on your presentation, which was very clear. So you started in the beginning by saying that the tests that we do with the current benchmarks are close to perfect. And then you dive into these research questions and consider how can we assess if the detectors are working well or not. A question out of curiosity, isn't this the case for an updated benchmark, or does not make sense to have it?
Like when the detectors are already aware of what is coming next, the performance is really good. Like because what they learn is the feature specific artifacts, and they're not learning the generalized features that needs to be there to detect the unseen attacks. So that is what's the point to evaluate the.
Can we create a benchmark that is able to test that features or that approach for these detectors?
There already are research where researchers have used multiple data sets while training, but still the generalization technique is not yet that strong to generalize unseen new images. So that's what the researchers have still so far reached.
Yes. Well, thank you very much for this open challenge still yet. Thank you very much.
Yes, thank you.
So now we'll move on to the next paper. We are going to move to paper 195, Zero Trust Architecture for 5G enabled mobile cloud computing, from Urvish Pandya and Sweta Pandya. Yes. And it is okay. So I'll ask you if you please, if you could keep this for 10 minutes, and I'll warn you after 9 minutes. Thank you very much.
Definitely. I hope you are able to hear me fine. Perfect. Thank you so much for confirming. Good afternoon, everybody. My name is Urvis Pandya and my co-author is Sweta Pandya. We are going to present a paper on Zero Trust Architecture for 5G-enabled mobile cloud computing, or you can call it MCC as well. So what we are going to cover today, we are going to start with the abstract that covers the core goals and the problem statement, the introduction, that evaluation of 5G and MCC, the literature review, the research gap that includes the limitation in existing security models, the proposed methodology, the simulation-based research that we have did, comparative analysis, perimeter-based versus zero trust, result and the discussion, focusing on the security and the performance metrics, conclusion and the future work of like what we found and what are the next steps and the references. So what we are planning to cover. The convergence, the merging of MCC and the 5G is essential for the next generation technologies like autonomous vehicles, remote healthcare devices. The problem that we are facing that the distribution or distributed nature of this 5G distributed standard security parameters making them outdated most of the time. So due to this dynamic technology changes, they are getting outdated within 6 months or 1 year. The solution, no matter which technology or which version of technology you're using, a zero trust architecture focusing on never trust, always verify, and list privilege access is possible solution that we are going to explore. The key metrics. We are aiming to enhance the confidentiality, integrity, and the availability while maintaining the optimal effective performance. Now, as part of introduction, the 5G potential. It offers the higher data rates and lower latency. It enables the smart cities and interactive multimedias. The new risk, it comes with use of virtualization, network slicing, and the mobile edge computing, creates the new attack surfaces. The perimeter failure, the traditional models assume the internal devices are safe, but the 5G environment face significant insider threat as well as lateral movement. Zero trust shift removes the implicit trust by continuously verifying users, devices, and the application regardless of the location. So, as part of a literature review, of what we learned that NIST 80207 and other security foundations, ZTA components but lack of specific details for MCC. The current research that focus on SDN, virtualization, MEC as major 5G attack surfaces are still in the research mode. The industrial IoT, the recent zero trust architecture applications have been tested in 5G industrial settings, but lack scalability for the general mobile scenarios. And the MCC focus itself. The existing MCC studies highlight the data offloading issues, but rarely include the continuous trust verifications. So the research step that we identified was contextual specifics. General ZTA guidance is not currently tailored to unique specific of 5G/MCC. The performance data, a lack of metrics exists for the real-time and mobile context, particularly regarding the latency. Scalability. The efficiency of ZTA for massive mobile device population, MMTC, has not been fully evaluated. And practicality. Many standards define capabilities but do not prescribe the actual ZTA enforcement models for MCC. So our proposed methodology focused on quantitative simulation-based design aligned with 5 core research objectives. Layer assessment, modeling the roles of mobile devices, 5G radio, edge nodes, and cloud infrastructure. The attack simulation based on testing unauthorized device access, DDoS attacks, and the insider resource capture. And comparatively designed, implementing both a perimeter-based baseline as well as a zero trust model in the same environment. When we did our comparative analysis, what we found out that for the trust assumption, internal network is safe versus zero trust model which focus on never trust, always verify. The authentication is a single access point versus under zero trust. We are doing continuous verification. Access control, blanket trust after login versus least privilege access. Decision type is static versus here is dynamic and the context based. So what we found out as a result, the authentication success rate, ASR, ZTA maintained the success rate about 94 to 98% across high user loads compared to 82 to 91% in the perimeter models. Unauthorized access detection, UADR, ZTA detected 95% versus 62 for perimeter. So insider attack, ZTA detected 93% versus 58. Combined attacks, ZTA detected 91% versus the 54% for the perimeter. The analysis that we came out was ZTA significantly reduced the lateral movement by eliminating the implicit trust. The second is the performance. So latency, we see that it increased a little bit for ZTA, 44 millisecond versus 39. Throughput reduced from 705 versus 730 Mbps, and the resource utilization was increased to 69% versus 63%. Conclusion and the future work. So ZTA is a robust scalable solution that enhances the 5G MCC security without violating performance needs. What we need to think about future, how we can use AI to adjust security policy based on the real-time behavior. Lightweight authentication, solutions for resource-constrained IoT devices. Energy efficiency, basically how we can minimize the battery consumption during the continuous verification. And edge testbeds, validating frameworks in real-world 5G platforms. And these are the references. So thank you so much. I'm happy to take any questions now.
Thank you very much for your presentation and finishing before time. Any question? Somebody wants to say something or make any comments? Well, I would not, if you allow me, I will just make a very brief overall question. So is how if you are saying that your zero trust architecture is a good approach to use on 5G networks, so what prevents the future of 5G networks from using a zero trust architecture? Is something that is easily included, or it needs some adaptation? Do users need? So where is the cost, if there is a cost, to consider this as a solution like the solution that you propose?
Thank you for this question. There are three factors that is constraining enabling the ZTA across all the mobile devices. So first is the cloud infrastructure needs to be supportive of all 5G environments on the backend side. Second is about number of mobile devices in the world. I believe there are 8 billion people in the world. So we are talking about at least 4 to 5 billion. Half of the population are using mobile or more than that. So we are talking about 4 to 5 billion mobile devices across the world. Implementing ZTA for each devices and keep that updated is a constraint. So that's why it's not easy. We are learning more about how the new security threats are coming up and how we are making sure that ZTA will keep them away from embedded or envisioning into the mobile devices. But the scale is the biggest challenge, as per my understanding.
Good. Thank you very much for your clarification. Just one final question. I didn't saw your affiliation. What's this
I'll
division?
add that in the slide. Yeah, I'll add that in the slide.
Can you just say?
Oh, yeah, we work for, me and Sweta work for different organizations. So that's why we did not put a single title on that.
Okay. You are not okay. You only say if you want. Okay. Well, Urvish, Panyam, thank you very much for your presentation. We'll move on now to the next one, to the next paper. The next paper is 235. the need for standardized evidence sampling in CMMC assessment, a survey-based analysis of assessor practices. This is going to be presented by Logan Thierrien and John Hastings, not the correct pronunciation.
Greetings. Can you see my screen?
No.
No. Okay. All right. All right. It's making me reboot. I'll be right back.
Okay. I hope that we have time. So the next paper is going to be paper 273, Chandra Shekhar Medisherla. Okay, it's here. Okay, the person is here. Okay. We'll wait just a little bit, if you don't mind. We'll wait just a little bit to see if Logan Terrian can come back.
I can wait.
You will be next. Saying thank you. I was just checking that you are here.
Yeah.
Thank you very much.
Thank you. Thank you.
So let's wait to see if the person, the author comes. Okay. If the author doesn't come, what we'll do is we'll switch the orders and you can start so that we don't take more time. Okay. Do you mind starting now? Wait, Logan is here. Is Logan here connecting?
I'm
Either
here.
works.
Very difficult connection on. Okay. Are you here with? Yes. Okay. Logan is
I'm
here
here.
with us.
Can you
Okay.
see my screen now?
Yes, we can see your screen now. So, okay.
Oh.
So, Logan, please, 10 minutes, 10 minutes for your presentation. I'll warn after 5. Okay.
Yes, sir. So
Thank
good
you.
afternoon. My name is Logan Terrian from Dakota State University, and this research is conducted in collaboration with Dr. John Hastings, who's present as well today. Today, I'll be discussing a critical and underdeveloped area within the CMMC ecosystem, and it's evidence sampling and level 2 assessments. This study examines how our assessors currently make sampling decisions, how much variability exists across those decisions, and what that means for the consistency and credibility of the CMMC certification process throughout the U.S. defense industry, which currently consists of about 120,000 defense contractors. So the cybersecurity model certifications, also known as CMMC program, is designed to assess defense contractor compliance with NIST SB 800-171 implementation requirements for protecting controlled unclassified information, also known as CUI, across the defense industrial base, and has only been formally implemented since about January of 2025. So it's a relatively new assessment framework. There are 3 assessment levels in the CMMC framework. At the level 2, organizations must undergo independent third-party assessments conducted by CMMC third-party assessment organizations, also known as C3PAOs, which evaluate the implementation of, again, NIST SB 800-171 requirements. Level 1 of the other 2 levels, level 1 is considered a low confidence self-assessment performed by the contractor. And then there's level 3, which is considered a high confidence assessment performed by the Defense Industrial Base Cybersecurity Assessment Center, also known as DIBCAC, which is an organization within the Department of War. These assessments are expected to demonstrate rigor, repeatability, and fairness. However, while the framework clearly defines what must be assessed, it provides limited direction on how evidence should be sampled to support these determinations. And this creates a gap between policy intent and assessment execution. So evidence sampling, of course, is fundamental to an assessment process. It determines which artifacts are reviewed, how conclusions are formed, and the level of confidence and compliance determinations. It also directly impacts assessment efficiency and duration, which can also be rephrased as time and money, a cost that will eventually trickle down to the U.S. taxpayer. If sampling is inconsistent, similar organizations may receive different outcomes. Assessments may take longer or become contested, and stakeholder confidence and certification results may decline. So while sampling may appear procedural, it's actually pretty central to the assessment validity. In mature audit disciplines, sampling is governed by structured methodologies. These include risk-based models, defined representativeness for criteria, formalized approaches to determining sampling size. Formalized CMMC assessor training, however, does not include sampling methodologies or practices. A history of assessment experience is required to become certified as a CMMC assessor, but the only qualifier that requirement is the amount of time performing assessments, not specific knowledge, skills, or abilities. In contrast, the CMMC assessments often rely on individual assessor judgment, informal practices within organizations, and unstructured decision-making. This lack of standardization introduces variability that is difficult to measure and even harder to defend. This study was designed to better understand what that variability is. The research makes three key contributions. First, it provides an empirical snapshot of how evidence sampling is currently performed by CMMC assessors. Second, it uses scenario-based analysis to evaluate how assessors respond to identical conditions. And then third, it captures practitioner perspectives on whether standardization is needed. Together, these contributions help determine whether sampling represents a methodological gap in the CMMC assessment process. The study is guided by three research questions. First, what factors drive sampling decisions in CMMC assessments? Second, how much variation exists among assessors when evaluating identical scenarios? And third, how frequently do assessors experience inconsistencies across assessments or across different C3PAOs? These questions are designed to move from anecdotal observation to measurable insights. This study uses an exploratory mixed methods design. It combines quantitative survey data with qualitative thematic analysis. Data was collected through structured survey responses, scenario-based questions, and open-ended explanations. This approach allowed us to capture both observable patterns and the reasoning behind assessor decisions, which is especially important when studying professional judgment. The survey targeted CMMC assessors and lead certified assessors. So just for background, to be qualified or to be certified as CCA, you need 3 years of cybersecurity experience, 1 year of assessment or audit experience, and hold an entry-level certification such as Security Plus or equivalent. And then to become a lead CCA, 5 years of cybersecurity experience is required, along with 5 years of management experience, 3 years of assessment or audit experience, and a higher level as certification such as CISA or CISSP. As you can see, the requirements for having that assessment or audit experience are pretty low, even compared to the rest of the experience required. It did include questions on experience, sampling practices, decision drivers, and scenario-based decision-making, perceptions of inconsistency, and views on standardization. Importantly, the questions were aligned to establish concepts in audit sampling and cybersecurity assessment practices, and this ensures the study is grounded in both theory and practice. The survey was distributed via email to assessors identified through the CyberAB marketplace. The CyberAB is the accreditation body for C3POs and partly responsible for the assessors themselves, their certification process. Of those identified, a total of 556 potential participants were identified and contacted, but out of that, only 17 usable responses were collected. While the sample size is relatively small, it does reflect the targeted population of experienced practitioners that we were looking for. And the goal of this study is the exploratory insight rather than statistical generation. So it works with what we needed. The respondents represent a highly experienced group. Over half of them had more than 10 years of cybersecurity audit experience, and nearly 60% have conducted more than 10 CMMC assessments. Again, because this started beginning of last year, those are pretty large numbers compared to what is actually occurring. I think we're a little bit over 1,000 assessments at this point, a year later. This is important because it indicates that the findings reflect practices of seasoned professionals rather than entry-level assessors. One of the most significant findings is the lack of formal sampling methodology. 71% of the respondents reported that their C3PO does not provide a defined sampling approach. Additionally, nearly half indicated that existing guidance provides no meaningful direction. As a result, sampling decisions are often developed independently by assessors or small teams, and this leads to decentralized and inconsistent practices across the ecosystem. When assessors make sampling decisions, they rely primarily on heuristic factors. The most common drivers include environment size and complexity, assessor experience and judgment and perceived risk or control criticality. Very few respondents reported using formal statistical sampling methods. And that indicates that sampling is largely judgment driven rather than structured or standardized. To evaluate variability, assessors were presented with identical scenarios and asked how much evidence they would sample. For a medium-sized organization, responses ranged widely from very small percentages to nearly full population review. Some assessors avoided using percentages altogether. And this level of dispersion demonstrates that there's no shared baseline for what constitutes sufficient evidence. And this is one of the strongest indicators of inconsistency in the study. Assessors were also asked about their real-world experiences. The majority reported encountering inconsistencies either frequently or occasionally. And these inconsistencies occur both between individual assessors and across different C3POs, because there are some cases where C3POs don't have enough assessors, so they subcontract at a 1099 those CCAs to come work for them. So these CCAs have seen and experienced across multiple of those environments. And this suggests that the variability is systemic rather than isolated. In conclusion, the study identifies evidence sampling as a significant methodological gap within CMC assessments. Current practices rely heavily on individual judgment, and substantial variability exists even under identical conditions. Practitioners consistently recommend the development of a risk-informed sampling guidance, clear definitions and evidentiary sufficiency, and improved assessor training. Future work will focus on developing and validating a standardized CMC evidence sampling framework and testing it in real-world environments. And then ultimately improving the sampling consistency is critical to strengthen the credibility, scalability, and defensibility of the CMC program. Open for questions.
Okay, thank you very much for keeping the time.
Sure.
Are there any questions? Okay, then if not, thank you, Logan, for your presentation. We'll move to the next paper. Then it's paper 273, adaptive index selection for IoT vector databases. It's going to be presented by Chandrasekhar Medisherla. I hope the pronunciation is acceptable. Thank you very much. So again, I'll just ask you, please, for the 10 minutes presentation, and
Yep.
you may start. Thank you.
Yeah, sure. So meanwhile, I start presenting. First, I would like to thank all the session chair and the reviewers for thorough reviews, and the session chair for giving the opportunity to make this happen. So without any further ado, let me share my screen. Do you see my screen? Yeah.
Yes, we see.
So yeah, today, first of all, good afternoon and good evening, everyone. Like today, I'm going to present adaptive index. Adaptive index is a practical machine learning system that automatically optimizes vector databases for IoT edge deployments with all my quarters. So who contributed for this? So then this is a joint work with my colleagues from the industry and the academia. Our paper addresses a critical problem in the IoT infrastructure, causes millions of dollars in failures every year. So let me start with why this matters. Like these are three real production failures we documented here. So first is like an e-commerce company, search engine crash during the Black Friday, busy peak times when their index consumed all memory when a crash traffic spike, approximately, lot of revenue loss right during that time. The second is a semiconductor fab missed an equipment failure alert because their index sacrificed accuracy for memory, resulting also a huge financial loss. And third is a smart cities traffic system violated SLAs during monitoring rush hour, requiring expert intervention, which may take 30 plus minutes. The common thread here, if you observe, like all used vectors databases with static configuration that couldn't adapt to changing based on the workloads, what it is going through. So quick background for those unfamiliar with vector database. They power modern our IoT applications by storing data as high dimensional vectors, as illustrated here. When you search for a like a key search like a red sports car in a e-commerce site, or a query similar sensor patterns in the smart cities, right? So vector database find the nearest matches and give you appropriate result for you. So they are critical infrastructure powering everything from product recommendation to industrial monitoring, healthcare diagnosis. You know, so the fundamental problem here choosing between the indexes, right? Like those might be who familiar with vector databases. There are two kinds of indexes, right? HNSW, which is a hierarchical navigable small workload graphs, gives you great accuracy, over 95% if I recall correctly, but uses massive memory and crashes under high loads, right? So like another index type is IVF flat, inverted file flat vectors, is in memory efficient, which consumes low memory and handles traffic spike as well, but it sacrifices and the 10 to 15% accuracy. Which should you use, like, on well, it depends on the current workload, low traffic, or use HSNSB for quality, or high traffic switch to IVF to survive. So but here is the catch, right? Workloads change throughout the day. Smart cities see like a 6 to 8% variation between rush hour and midnight. So e-commerce has flash sales like to 10 cross or 15 cross spike during the peak time, right? So manual switching requires experts, and it takes more than 30 minutes. That's too slow and too expensive for the organizations. Adaptive index like solve this through autonomous adoption. Like it continuously monitors 18 features about the workloads, things like query rate, memory pressure, and data characteristics. So our lightweight ML model decides which index is optimal, then safely switches within 40 to 60 seconds based on the workload. So the key innovation, like is runs entirely on edge gateways, no cloud infrastructure or the expensive or no external dependencies needed. It's just a small model with a 4 millisecond inference time. So it works on commodity hardware. So our main technical contribution is identifying what to monitor. Okay, we engineered 18 features across three categories. Like query patterns tell us about current load. We see in 30 queries per second, or for like 400 plus queries per second, right? So data characteristics reveal the structure, right? Is the data naturally clustered, or making IVF effective? Those kind of areas. And performance metrics, the third category, it tracks system health, right? Is memory is pressured more than 80-85%, and is it about to crash? So unlike a black box deep learning, these features are interpretable. Operators can see exactly why the system made each decision. This builds trust and enables debugging. So let me walk through a typical day. Like example, at 8 a.m. low traffic, 30 queries per second, plenty of memory. Adapt index keeps HNSW type index running for maximum quality. And at 9 a.m. morning rush hits like 400 plus queries per second, memory climbs to 87%. The system detects this and switches to IVF within 60 seconds, preventing crash. So by 6 p.m. again, traffic drops again when we switch back to the HNSW for better search quality. So this happens automatically every day without any human intervention. So we validated this adapt index in two ways. First, controlled experiments on our data sets, including standard benchmarks like SIFT 1M, and our own synthetic IoT workloads. Compared static HNSW, adapt index achieves 29% better latency, More importantly, it beats simple rule-based approaches by 17%. The key is, continuous adoption based on real-time features, not just a simple, kind of guessing or, So, but the real proof is right. Like we implemented in a couple of low kind of severity production things. So we deployed across 47 edge gateways spanning 12 geographic regions. So over 90 days, serving 5 million queries daily, we achieved a 29% latency improved and increased uptime from 96% to 99%. That eliminated eight outages that would have cost more to the company. The system made 47 index transitions with zero failures. This is indeed such a prototype which we can test it, which is running well. So how did we achieve zero failures through defense in-depth safety mechanism? Transitions happen in four phases. Like first, build a new index in the background, zero impact, no live queries. Second, validate the test queries. If it's slower, about immediately. Or in the third phase, gradually shift traffic, start from 5% to at a time. Any problem triggers automatic rollback within 10 seconds, right? Fourth, the final phase, clean up the old index. This is just ML making decision. It's something engineering where multiple safety nets through way it is taking decisions. So three key lessons from what we observe. The first is the interpretable features. Engineering meets complex models. We tried neural networks. They were slower, needed more resources, and didn't improve accuracy. Simple features like query rate and memory pressure work great, and operators trust them because they understand them, right? So second is safety matters more than speed. Our 60-second transitions feel slow, but we had zero failures. Like automatic rollback saved us twice when network issues caused false readings, right? Third is economic drive real world adoption. Our engineering team loved the technical results. Management loved the numbers, how much cost savings, quantify return on investment is, essential for all production enterprise systems. So
To finish,
here
please.
coming to the limitations, I'll be honest here. Currently, we support three type of index. With the FAS library, product quantization could reduce memory to 4 to 8, but we haven't integrated it yet. Our approach works for ready heavy IoT workloads, but not write heavy, scenarios. We need 60 seconds of monitoring data before making decision. That's too slow for flash events. Future work includes supporting more index types, federated learnings across multiple deployments, and faster decision making. We're also exploring disk-based indexes for billion-scale data sets. So these are the key takeaways.
Finish.
With that, I'm happy to take questions.
Okay. Thank you very much for finishing now in time. Does anyone want to make a question to the author? Well, okay. Well, I just have to say thank you for your presentation. It was an interesting result. I understood from your presentation that you did a production setup. Yes. Can you just talk a little bit of what was the case
It's a
for
right,
everybody?
and see, right, autonomous way you have to switch right to seamless experience customer make it happen. So this manual between the based on the workloads, it's hard to somebody human intervene and take a switch and everything. It more timing and cost efficient. So that's why we come up with this approach. We using a very lightweight model, gradient boosting, XGBoost. We can use which is just 12 MB. We are using it. It's
Okay.
working like as expected.
Okay. Thank you very much for your presentation.
Thank you.
Now we'll move to the next paper, so that we can keep on time. It's paper 339, malware classification on PE files using deep neural networks. The work is going to be presented by Daniel Vilaça and Luís Ferreira. Yes, please.
Can you hear me? Check. Very nice, thank you. 1 second. So, hello everyone. Thanks for being here today. My name is Daniel. I will be sharing our recent research that I've been conducting alongside with my professor Luís Ferreira at the Applied Artificial Intelligence Base Labs. More specifically, our work in malware classification on portable executable files using deep neural networks. 1 second here. Okay. Here is a quick roadmap of this presentation. I'll start with some contextualization to frame out the problem. Then we dive into our core state-of-the-art concept, representing malware as an image. From there, I'll walk you through our methodology and share our results. Finally, we'll cover our optimization techniques, wrapping up with our conclusion and future work. So starting up with the context, let's look at a typical social engineering attack chain. In this case, a 2025 click fix or file fix scenario. It generally starts with the setup, which you can see in the top left corner. The attacker places a lure, like a fake software update, and drives traffic to it via phishing emails or malvertising. Once the victim lands on the page, we enter the trap. The website uses social engineering to trick the user into following a set of technical instructions. The victim thinks they are fixing an error, but they are actually deceived into manually copying and running a malicious command, often with something like PowerShell. From there, we hit the execution phase, and the initial command silently reaches out and pulls down the actual payload, which could be a rat or an info stealer. The ultimate outcome, the system is compromised, and the victim's private data ends up being sold on the dark web marketplaces. Our focus in this work is how we analyze and classify those payloads once they hit the system. What makes these modern threats so difficult to manage? First, the exponential growth, often new variants, creates a massive analysis bottleneck. Traditional manual reverse engineering simply cannot scale anymore. Combine that with the staggering financial impact of these incidents and the rise of AI evasion techniques used to bypass standard defenses, and it's clear that we are losing the arms race. This brings us to why we need a fundamentally different approach. As we move into the state of the art, let's quickly establish our scope. We all know fundamentally the definition of malware, any malicious code designed to harm, disrupt, or infiltrate the system. But for our purpose of this research, we are strictly focusing on portable executables, or PE files. As a quick reminder, this is the standard file format used for Windows for its programs and system libraries. Most commonly, what you see as your standard .exe or .dll files. So how do we actually analyze these PE files using neural networks? To analyze these files, we build on a foundational concept introduced by Lakshman and Nataraj in 2011. The paper was called Malware Images Visualization and Automatic Classification. We simply convert the raw executable binary directly into a 2D grayscale matrix, where each byte maps to a pixel intensity. This is powerful because malware from the same family reveals unique, highly identifiable visual textures. You can see some of those distinct structural patterns here in this collage. These are some examples of malware-generated images from the dataset that we explore in this work, the Malin dataset. which provides us with 25 distinct malware families with close to 10,000 images. As you can see from a few examples in the table, spanning across dialers, Trojans, and worms. The key advantage here is that variants from the same family retain highly consistent visual layouts. This structural similarity is exactly what allows us and our neural networks to perform effective pattern-based classification. And this brings us to the section 3. This methodology applied in this work consists in a pipeline that follows 5 core steps. We start with binary to image conversion, shaping the 8-bit vectors into 2D matrices. Next is resizing normalization to get a standard dimension using bilinear interpolation. Since VGG16 expects a color image, we perform a pseudo RGB conversion by replicating the grayscale channels. This set us up for our core experiment, comparing a baseline CNN trained from scratch versus VGG16 using transfer learning. And finally, we ensure robust results through a strict model optimization. Looking directly at this comparison between baseline CNN versus VGG16, the advantages of transfer learning is clear. VGG16 pushed our overall accuracy to nearly 19% and dropped the error rate to just 1.12%. But the most critical takeaway is at the bottom of the table. Here you can see the specific recall for tricky malware families. VGG16 caught 100% of the autorun.k variants, which the baseline missed entirely, and nearly double the detection rate for Switzer. To achieve those metrics, our optimization strategy relied on a few specific concepts. First, we used stratified k-fold cross-validation to ensure our model evaluated fairly across all malware families, regardless of class imbalances. For the VGG16 training, we used a two-stage approach. We started with a warm-up phase with a frozen base to stabilize the weights, followed by a fine-tuning where we unfroze the top block so the one network could learn the high specific textures of our malware images. Moving straight into the next section, let's look at the actual results of applying that stage optimization protocol. When we compare the standard transfer learning against our optimized model, the impact is significant. By shifting from a simple frozen base to our warm-up plus fine-tuning strategy and dropping the learning rate to 1e minus 5, we pushed an overall accuracy to 99.33%. But more importantly, this stabilized the model across the board. So our lowest accuracy dip during cross-validation jumped from 89% to a much more reliable 97%. We also wanted to see how this optimization handled those tricky families we mentioned earlier. Looking at the recall, autorun.k maintained its perfect 100% detection rate. But for the Switzer variant, which is notoriously difficult to classify, our fine-tuning delivered a solid 8% gain, bringing its recall up from 0.65, so 65%, to 73%. This brings us to the final section of our presentation, our conclusions and future work. To summarize our findings, our tests clearly show that transfer learning should be preferred strategy over training models from scratch. We also proved that with optimization, we can achieve significant gains, like the 8% boost when we're dealing with notoriously difficult small malware families. However, we did identify a resizing problem. Forcing files into a fixed image size causes information loss, particularly in high entropy sections. Because of this, our future work will also focus on exploring a paper called spatial period pooling to solve that issue. Moving forward, we also plan to expand into entropy and obfuscation detection, creating a binary gatekeeper system, expanding our dataset, and ultimately focus on real-world implementation and deployment. And with that, I'd like to say thank you for your time and attention today. If you have any questions, feel free to ask. I will try my best to answer them.
Mhm.
I will also leave our socials below in case someone would like to get in touch.
Okay.
That's
Thank
it.
you very much for your presentation, Danielle. So does anyone has questions that wants to make? Well, it's an interesting work, but considering the time, I will move to the next presentation if there are no further questions from the other peer persons. Thank you very much. So we'll move to the next paper, which is paper 409, Selective Memory Sharing in Multi-Agent LLM Teams via Agent Gym RL by Bavuk Jain. I hope that, yes, you are here.
Hi. Yeah,
Hello.
I'm on the call. I'll just go ahead and share my screen.
Yes, please. And so you already know the time. It's 10 minutes. I'll warn you after 9 minutes in case you don't reach the conclusions.
Sounds good. Just give me a second.
Yes.
Okay. Can you see my screen?
Yes.
Okay.
You
Hi
may start.
everyone. Thanks for being here. So today I'll be talking about selective memory sharing in multi-agent LLM teams, a problem that becomes critical as we move from single LLM systems to collaborative agent-based AI systems. This work focuses on a key question: how should multiple AI agents share memory efficiently without degrading performance? We'll explore why naive memory sharing fails, what we propose instead, and how it improves system behavior in realistic environments. First, let's make the problem very concrete. What you're seeing here on this slide are the two extremes of how current multi-agent systems share information. On the left side, we have full sharing. Every agent shares everything with every other agent. Now, at first glance, this sounds great. More information should mean better decisions. But in practice, this creates too much communication. Agents get overwhelmed with irrelevant information, and the system becomes noisy and inefficient. So, more sharing actually starts to hurt performance. On the right side, we have the opposite extreme, which is private memory. Here, agents don't share anything at all, and each agent works in isolation. This avoids communication overhead, but now agents lack context, they duplicate work, and coordination breaks down. So, here, the problem is not noise, it's lack of collaboration. So, what we end up with is a clear tension. If we share everything, there's overload, and if we share nothing, there's poor coordination. And that leads us to the central challenge of this work: how do we find the right balance between these two extremes? Because that's where effective multi-agent systems actually live. Okay, so now that we have seen the extreme, let's look at what current systems actually do, and more importantly, what they don't do. First, most existing systems don't really solve this problem. They simply pick one side, they either share everything or they don't share at all. And there's no real attempt to find a middle ground. And second, memory is usually treated as a fixed design choice. It's something you set once and then forget about. But that's a problem because in reality, memory directly affects how agents behave, coordinate, and perform. So it shouldn't be fixed, it should be something we actively optimize. Third, and most importantly, there is no clear method today to decide what information should actually be shared. Not all information is useful. Some of it, for instance, creates noise, increases cost, or even harms decision making. So, if we step back, the real gap becomes clear. We don't have a principled way to decide what to share, when to share, and why. And that leads us to the key question of this work: can we share information in a smarter way instead of just sharing everything or nothing? And that's exactly what we try to answer next. So we call it selective memory sharing. The core idea is very simple. Agents should not share everything. They should share only what is relevant. What does selective sharing enable? Two main things. First, agents share only relevant information, which reduces noise and avoids confusion. And second, they avoid unnecessary communication, which improves efficiency and reduces cost. And to make this more concrete, let's compare all the three approaches you see here. First, on the left, we have private memory, no sharing, which leads to poor coordination. In the middle, we have full sharing, everything is shared, which leads to too much communication. And on the right is our approach, which is selective sharing. Only important information is shared, which gives us best of both the worlds. That is, it's more efficient and well coordinated. So the key intuition is we don't need more communication, we need better communication. And that's the principle we built on in the rest of the work. So let me walk you through how the system actually works. At a high level, we have three agents: the planner, which decides what actions should be taken, the executor, which carries out these actions, and the critic, which evaluates whether the outcome is correct or not. Now, in a typical multi agent system, these agents would directly share everything with each other. But in our setup, we introduce a shared scratch pad. All agents can write to this shared space. So the planner can store its plan, the executor can log actions, and the critic can provide feedback. This creates a central place for coordination. Also, not everything written gets stored. We also introduce a component called the memory controller. This sits between the agents and the shared memory, and its job is to filter incoming information and decide what is actually worth keeping. So instead of blindly storing everything, we store only important task relevant information. And this does two things. First, it reduces noise in the shared memory. And second, ensures that agents only see useful context. As a result, the system becomes more efficient, more coordinated without increasing communication overhead. And this idea of controlled memory flow is what enables selective sharing in practice. Now that we have defined the system, the next question is how do we actually evaluate whether it works? We focus on three key dimensions: task performance, which measures how often the agents make correct decisions; second, coordination quality. Here we look at whether agents agree with each other; and third, communication cost. This measures how many tokens are being used. Now let's look at what we actually observe. First, and most striking, we see a 35 to 55% reduction in communication cost. That means almost half the tokens are eliminated, so the system becomes significantly more efficient. Second, we see a 20 to 30% reduction in contradictions, which tell us something important. Agents are not just talking less, they are actually agreeing more, so coordination is improving. Third, we observe a 4 to 8% increase in accuracy, and while that number may seem modest, in already strong systems, even small gains are meaningful. And finally, we see a 6 to 12% improve in success rate, which reflects overall task completion performance. This is important because typically reducing communication hurts performance, but here we show the opposite, that is, sharing less but smarter actually makes the system better. Now, now let's step back and understand why we see these results. This figure shows the relationship between communication costs on the x-axis and coordination quality on the y-axis. Starting on the left, we have private memory, very low communication, very poor coordination. Agents simply don't have enough shared context to work together. And on the far right, we have full sharing. And beyond a point, more communication adds noise rather than value. So what we see is a diminishing returns curve. As communication increases, coordination improves, but with decreasing benefit per additional cost. But our approach, selective sharing, it sits in the middle. It achieves strong coordination, but at a much lower communication cost. Now, another important question that we try to answer is, does this approach generalize beyond a single task? So we evaluate across multiple domains. First is web navigation, which involves sequential decision making, interacting with dynamic environments. Second is text-based tasks, which are more reasoning heavy and language-driven tasks. And third is scientific workflows, which involve structured multi-step processes where connectness and coordination are critical. These domains are quite different from each other. They vary in structure, complexity, and interaction patterns. And across all of them, we observe a consistent trend. Selective sharing reduces communication cost while also improving task performance. So, the key takeaway here is this is not a task specific behavior, it's a general pattern across different types of problems, which makes selective sharing a strong candidate for real world multi agent systems. Now, while the results are strong, there are important limitations and insights as well. First, not all filtering strategies are effective. Simply deciding to filter information is not enough. How you filter matters a lot. Second, we observe that simple heuristics like truncation or selecting recent messages actually degrade performance because they discard important context and keep irrelevant information. And this leads to a key insight. The problem is not reducing information, it's selecting the right information. Third, effective selective sharing requires intelligent task aware selection, and the system needs to understand what is relevant in the context of the task. So, if we summarize the main takeaway, quality of information matters more than quantity. And this also highlights an important direction for future work, designing better memory controllers and possibly learned or adaptive mechanisms to identify what should be shared. To conclude,
1 minute.
our work shows, okay, uh, I'll just conclude quickly. Our work shows that memory design plays a central role in multi-agent LLM systems, and we demonstrate that selective sharing provides a strong balance between efficiency and coordination. Thank you.
Thank you. Right on time. Thank you for your presentation, Bavuk. Any question that somebody wants to make?
Yeah, I have one.
Please.
Okay, thank you, Babuk, for your presentation. I don't know if I realize well your work, but I think you mentioned that only relevant information will be shared. Can you explain, please, what kind of criteria did you use to classify what is relevant information?
Bavuk,
I'm sorry, can you repeat the question once again?
Okay, basically, can you share with us what was the criteria you have used to classify as relevant information to share?
Right. So in our work, relevance is not defined statistically, but it's task dependent. So like at a high level, we use three criteria to decide. First, task contribution, which is basically, does this information help move the task forward? That is planner decisions, key intermediate results, verified outcomes. If it directly impacts the next step, we keep it. The second, cross agent utility, that is this information useful for other agents? For example, a plan is useful for the executor, feedback is useful for the planner. If it improves coordination, it considered relevant. And third, signal versus noise. So we filter out redundant information, low confidence outputs, and verbose reasoning that does not change decisions. So basically, in our work, relevance is defined by utility.
Thank you.
okay. If there are no further questions, I'll move to our final paper. It's a long session, and this is the last one. So paper 488, comparative study of symbolic execution tools applied to vulnerability detection. It is going to be presented by André Cardoso. André?
Screen? Sorry. You can see my screen?
Sim.
Okay. Hello everyone. I'm André Cardoso. and I will be presenting to you my work on the comparative study of symbolic execution tools when applied to vulnerability detection. I will jump very quickly through all topics. I'll introduce very quickly security testing, what techniques there are, the objectives that we are focusing with this comparison, the tools that we observed and selected, the experimentation that we did on the selected tools, and the conclusion that we got from the results of the experimentation. Inside security testing, there are two most common techniques, static and dynamic application security testing. This work will focus on symbolic execution, so that falls under static SAS. The three main pillars of symbolic execution are constraint resolution, path explosion, and environment modeling. So first, constraint resolution refers to the computation of variables that may impact the program flow. Whenever a variable can result in one or more paths, possible paths in a application logic, this may result in each new path may result in much more of their own, which will then cause a problem known as path explosion. The possibility of an exponential increase, which will then create a lot of issues for symbolic execution. We also have then environment modeling, which helps the tools to have a deeper comprehension and know which paths to explore or to ignore with more certainty. With environment modeling, we let the tool know of direct dependencies like libraries of the programming language or wherever, or even indirect dependencies like OS utilities on which the application will run. So in this comparison, we will primarily look at accuracy metrics like true positives, true negatives, false positives, and false negatives, which will help us calculate a Uden index, which will serve as a comparison of the tools. In terms of performance, we will look at the paths traced by each tool and try to correlate them with the time of execution for each scan and CPU and memory usage of each tool when testing the programs. Also, for complexity of the vulnerabilities that each tool is able to find or not, if the tool is customizable or not as well, and how hard it is to customize and adapt the tools to each application and to each use case. So these are the tools that we considered, that we found and considered for this comparison. On the left side, we have tools for Java and JavaScript, Symbolic Pathfinder, and Java G2 and SimJS. These are interesting, especially because of the very common project known as WebGoat, which we would definitely like to study here. But on the right, we have the platforms LLVM and WebAssembly with Cloud9, Kite, CLI, and OE. We selected CLI and OE based on a lot of criteria, but we will focus on them for now. Don't want to get too long on it. Despite CLI and OE are being designed to different architectures, CLI for LLVM and OE for WebAssembly, both support symbolic execution for C, C++ applications. So we can compile C for an LLVM architecture and WebAssembly. I will show you the 4 of the samples that we tested. these four cover different vulnerabilities, very small sources, very simple, just to test how the tools behave with these sort of vulnerabilities. Starting with global buffer overflow, we see that CLI was able to CLI traced 5 paths. This shows us how simple the flow is. OE doesn't show us any information regarding that. It's, let's say, a limitation of the tool. But regarding resource usage and time spent, they are not very far apart, despite OE not being able to find the vulnerability. This scenario is shared across the other vulnerabilities like stack-based buffer overflow, null pointer dereference, and use after free. The resources across these four vulnerabilities are very similar, and if we pay attention, OE wasn't able to find any of them, and CLI was. A bonus sample that I decided to include specifically because the time of execution and resource usage was very low. It's the regular expression matcher. It's not. It doesn't try to find specifically a vulnerability, but instead a bug that triggers a bad execution. And in this test case, we see that CLI traced over 6,000 paths. Again, we have no number on the OE side to compare, but we do know that OE had a much larger consumption of resources and an even larger consumption of time, and wasn't able at all to find the problem that CLI found. We can see here the comparison of time from 13 seconds on CLI side and 900 seconds on OE side. A brief conclusion. The points that play in favor of CLI is how mature it is. It's a tool that, comparing to OE, has a lot of years in usage, a lot of developers behind it, a lot of discussion online around it. OE, on the other hand, is in early development and not so much discussion. CLI showed a lighter resource usage, a slower baseline. Despite that, it's probably because it prepares the scan with more information than OE does. That leads to a worse analysis by OE and a lower detection rate, which then leads to a lower index of UDAN. CLI has a 54/29 of OE. A big important notice is that CLI is focused for symbolic execution. It's his main area of development, while OE focused to be a WebAssembly toolkit that also implements symbolic execution for multiple languages. I hope I covered everything. Thank you. If you have any questions, feel free.
Okay. Thank you very much, Andre, for finishing before time. Thank you very much. Does anyone want to make any question to Andre? No. Okay. I don't have questions because I'm one of the authors of this work, so I already met the work in Andre also. Well, so I think we are in considerations to finish this session. I want to thank you all the authors for being here, for presenting in time, and for presenting within time, and for staying here for the event until the end. And thank you very much for all. I hope that I'll see you next year, either at the conference or at our specific workshop. One of those will be nice because we'll see each other again. So if there are no final comments, well, I would like to just thank you for your participation and
have one
wish you
question.
a good event at the conference for the other sessions.
Sorry, no, no,
Luis
there is
wants
a
to say
there is
something.
a question in there.
Yeah. Hey, no. My paper ID is 7. So what is the slot to give that presentation of that paper ID 7? Paper ID 7.
Paper 7.
Yeah.
Okay. Paper 7.
Paper 7 in the next session. Next session is starting soon.
Okay.
It's in next session. We are still
Yes,
finishing
next
the
session will be
first
starting in 5
session.
minutes.
We
Yes,
are
we are going to
11
start.
minutes late.
Okay, got it. So because I
Sorry.
joined now and
This is the previous, not the one after. Oh, I'm sorry. I tried to be as fast as I could. Okay.
No worries,
Well,
no worries. I'm
for all
absolutely fine.
our authors, thank you very much. We slipped a little bit on time, but still it was close enough and it was enough for everybody to present. Well, thank you. And now we'll have to leave the session open for the next session. Okay. Well, thank you very much. I hope to see you soon again.
Thank
Goodbye
you.
to
Thank you
all.
very much, Dr. Nuno.
Goodbye.
See you next year,
Goodbye.
hopefully.
Bye-bye.
Tchau, Nuno. Obrigado.
Thank you.
Yeah.
Yeah, so Srini, are you there? This is Sanjay.
Hello, Sanjoy. This is Murat Karabatak. I am the one
Hey,
of the organizers.
Sanjay.
I
Nice
think
to
we
meet you,
can
Sanjay.
start the session in 5 minutes, rather. In 5 minutes.
Okay,
Okay?
should I start
Okay.
in 5 minutes? Okay, that's fine.
Maybe,
Yeah.
yeah, because session starting 4:45.
4:45, yeah, just in
Okay.
next 2 minutes, but yeah, I can wait.
Yes.
I have joined,
Okay.
so
Thank you.
to make sure that, yeah, sure.
Hi, Sanjay. Are you able to hear me?
Yeah, I can hear you.
Okay. Just one thing to add. At the end of the presentations, please send us an email, not only indicating which presenter was the best throughout this session, but also the paper IDs who were not able to
Yeah,
present.
sure.
Okay. Okay. Thank you so much.
Yeah, no problem. Thank you. So yeah, means we can start with Srini. I think your paper number is 7. Srini, are you there?
If a particular presenter is not here at the moment, I suggest that we move with the next presenter, then we can always go back and check if they show up a
Okay,
little bit.
sure. Okay, sure. So next is the paper ID 50 with Kendall, Standridge, and Asaf. Anyone is there? Okay. So next is
I'm there.
yeah, next is paper ID 90.
Are you
Joel
coming
D. Molina.
Sanjay, one question, sorry. Are you coming from the order
Yeah.
wise? Okay.
Oh, Shrini, you came? Yeah, because
Yeah, I
I
came.
was looking for you, but
Oh, okay.
you did not respond, so I was just going to all and all. Okay. But
Oh,
yeah,
okay.
we can start.
Maybe
Your
you
paper
already
ID is
called
set.
out. No, you already called out.
No,
Next,
we
I'll
can
go.
start with you. Nobody has responded, so we can start
Oh,
with you, Shrini.
perfect, perfect. Let me share my screen and let me open PDF. Okay. Hope you can see my screen.
No, I cannot. Yeah, now I can see. Yes.
Okay. Hey, I'm Srinivas Lugajula. Today, I would like to present my paper. That's a paper ID 7. It's a two pillars of banking intelligence that is pretty much developed based on artificial intelligence techniques and fraud preventions and churn mitigation purpose. We developed this research and yeah, I'm going to the next one. Conference. See, here is the one. There are two pillars, as I said. Like first pillar is fraud detection. Second pillar is a churn mitigation. Um, Before I go with the pillar one and pillar two, I'll give that brief introduction about myself. Like, I have been working from last 15 years in a banking side and financial side. As part of that, I thought to start and, investigate like, what can we make it better in terms of reducing the frauds, in terms of, churn mitigation point of view. Because in churn mitigation point of view, the customers or users frequently changing the banking services from one bank to another bank, and sometimes they don't like the banking services because of like different kinds of threats, like different kinds of attacks, some hackers kind of attacks, some like logging issues, session issues. Based on that, other hackers they might try to steal the data, and then they may try to use that funds and they can transfer that purpose. So started investigating and what we can make it better in terms of reducing this fraud detections, as well as reducing the customers to move from one banking service to other banking service. Instead of that, how we can retain them. That is the purpose of this one. With my last 15 years of experience, I have been observing this is a extensively. That's my 15 years experience I am putting here, and I am doing my presentation and my research here. I'm sharing as part of this. I came across with a real-time data as well as the test data. I'll in the next slides I'll give that brief overview. But let's go to that one by one now. I'm introducing the pillar one, that's the fraud detection. As part of this fraud detection, we are collecting the real-time transaction and we are comparing that risk scoring, and previously how we are used to get real-time transactions, how that fraud people are trying to use our data, how they are trying to transfer the funds. That part we compared with the real-time transaction, and we are identifying the risk scoring. Based on the risk scoring, we are providing this with the artificial intelligence, we are collecting the data and we are giving that what solutions are best. As part of this, I have done that XG boost versus CNN LSTM models. And coming to the next one, balance false positive against missed fraud. So sometimes usually there would be a real frauds which are coming maybe in a different reasons based on that unexpected clicking the buttons, unexpected we are clicking some external attacks. So based on that, we it shows that whether it is a balance false positive or like true positives or false frauds. That all the things will come into that as part of the pillar one fraud detection. And a class imbalance makes a detection difficult. So as part of this, like we are collecting the in my research we collected 10,000 of different data sets and we are making that class balance, and based on that 70% data is using for that transactions purpose, and 30% we are using on test data. Based on that we are making sure like how that class imbalance is playing a crucial role in terms of taking the decision. When it comes to the pillar two, that is a churn mitigation, it is basically based on artificial intelligent models. Like we are identifying, we are predicting like what are the use cases usually user is disappointing and planning to move to that one service to another service or one bank to another banking. In that way, with the help of artificial intelligence, we are taking like odd models, and we are providing what is a suitable for that customers and how that customers will get happy. That is another one. And another one is like link intervention to customer value. We are taking that every regular intervals will take that feedbacks and will provide that what they need, and how that a customer is gets satisfied. That all the things we'll discuss in our pillar two. So as part of this research, that presentation, like we can say results are on fraud detection, and basically as part of this fraud detection, we are having two benchmarks. One is the fraud data sets, which are tested with almost real-time data, and another one is a direct comparison based on the XGBoost versus CNN LSTM models. So XGBoost is a pretty much fast. Because of that, we considered as part of my research. And here another actual outcome we can consider here. Churn remains the broader motivation, not the repeated experiment that we can consider. So as part of my message, I can say as a presenter message, treat this as a strong fraud detection study with clear relevance to a broader banking intelligence. Let's move on to the next slide. Here is Kaggle CCFD. As I said, we collected that 2,84,807 anonymized transactions, and out of this, with the Kaggle data set, like it's like 492 fraud cases we found, and we should I can say like out of that anonymized, it's a 1%. I can say it's a very highly imbalanced. And another one is a 590,000 records,
Srini,
which we
one
can.
thing, sorry to interrupt, Srini. You have only 2 minutes, okay, to complete
Okay.
your presentations. Okay.
I'll go a little faster. Yeah. As part of this, fraud share is the 25%. You can see in the right side, fraud data set distribution. One is a normal transaction. It is a 99% success. And the one out of this 100%, 1% is a fraud transaction. We can see here also IEEE CIS data set distribution also. It's like 25% fraud and remaining 75% is the non-transaction. Let's go to the next one. I don't have much time, so yeah. Um, and Yeah, here is the like you can say the preparing the data, rebalance and train and evaluate. Here is that preparing the data purpose. We are collecting the missing values and removing the IDs which are having the missing values, and uh, making sure your encoding categorized, and then we are collecting the normalization feature. Based on the normalization feature, we are collecting the data and we are giving and we are applying our models. And the rebalance is here, applying the smart. Smart is one of the technique, and reducing the majority bias and train more fairly. And here is the XG boost is like a baseline, and another one is a hybrid model like CNN. LSTM is the best model, and based on these models, we are tuning and we are eagerly, stepping up to make sure how that training is implementing as part of that research, and evaluating accuracy and precision and recall. These are like top compared to previous research models. And let's go to the next one. Here is the table is clearly shows that one as part of XG boost and CC FD, like it is giving the 98% accuracy, and whereas CCFD, CNN LSTM, which is our model, like I can say it is giving 99.78%. This entire it gives the best single result, I can say 99.87 F1 score on CCFD, and whereas a harder benchmark I can say 98.12 accuracy and F1 on IEEE. Like I can say CNN LSTM is a way ahead if you compare with other models. And going to the next one, here it is a confusion matrices. Like it reveals that error trade-off. You can see here clearly 428 and 447 and 447 again for XGBCC FD data set, which we considered. And as part of this, I can say the hybrid model, which it is basically it's a harmful. It reduces the harmful of misses while keeping that false alarms are very low. And here the recommendation I can say the gain is not only a higher accuracy, it is also a better balance between missed frauds and unnecessary alerts. And here is the curve, Narvosic curve. You can see as part of my research, I I collected that different kinds of based on my data sets. I collected CNN, LSTM on CCFD data, and another one is a CNN.
Srini,
Yeah,
I'm very sorry, Srini. Uh,
yeah. Last two
the
slides, and
time
I
is
have.
over. Okay,
Yeah,
so
I'm
I'm
completing.
extremely
I'm
sorry,
completing.
but
I'm completing.
yeah.
Here is the conclusion. Here's the takeaway. Fraud detection remains a core high impact AI problem for digital banking. And the second takeaway, I can say, across both the data sets, CNN, LSTM outperformed XG Boost and the extra baseline reported in the draft. And the third takeaway, I can say, is which is the our strongest conference message is I can say it's a reliable fraud detection contribution with a path towards a broader banking intelligence. If you have any questions, please feel free to reach my email ID. That's all pretty much, and I'm stopping my sharing. Sorry, I took a couple more minutes
Yeah.
additional,
So
Sanjay.
does anyone have any questions, team? So, okay. So yeah, thank you, Shini, for the presentation, and thanks a lot. It was a nice presentation. Yeah, thank you.
Thank you, Sanjay. Thank you, team.
Yeah. So now next, I'm looking for paper ID 50, optimizing resistive losses in transmission system via voltage level selection. Kendall D, Monroe, and Asaf Varol. Anyone is there? Okay. So paper ID 50, is anyone there so far? Okay. Next, I'm looking for Joel D.
Hello,
Molina,
I'm here.
paper ID 90. Yeah.
Right.
Yeah, hi
Um,
Joel. How are you?
Hello, I'm doing good. Just need to share my
Great, great.
screen.
Okay. Yeah. Yes. And Joel, just to let you know, means your presentation time is 10 minutes, and then we
Okay,
can have some quick Q&A session, just to let you know. Yeah.
sounds good. Okay. Can you all see the presentation?
It's coming up. Yeah, I can see.
Okay, perfect. All right, so my name is Joel Molina. I am a graduate student at the University of Nevada, Reno, And my research paper is on deterministic LLMs, a practical forensic framework for verifiable and reproducible local LLM inference. So first, giving a bit of the problem statement. Basically, the Daubert standard is due to a lack of bit identical results, LLM-generated work can be dismissed as hallucinations or speculative because you can't recreate it and it will always get something different. And the use cases of this within the digital forensics aspect is evidence triage. So when you take massive data sets of reports and try to summarize them using AI, or when you compile information across multiple reports, this is also unverifiable and unusable in court, meaning officially it shouldn't be being used by organizations or law enforcement agencies. Getting further into the problem, both cloud-based LLMs and local LLMs face certain problems. So cloud-based models, they're proprietary in nature. They're owned by the private companies, meaning you can't hash the internal weights or their states. You also can't reproduce their results because they have a non-zero model temperature, and you can't generally change this. For local language models, there are small variations in CUDA kernels or runtime libraries, meaning that you'd have to stay on the same system. There is numeric instability across non-associative floating point operations, and all that means is that if you ever quantize the model, say to floating point 16, brain floating point 16, or even further down, you can't guarantee determinism. Furthermore, if you try to optimize your model for things like continuous batching or prefix caching, this would also introduce non-determinism, with the entire point being that you have to stay at the most basic level of the model with its full weights and size. So some of the existing solutions to this problem include watermarking. That's where you modify output text with a secret signal just to try and get back that level of provenance. The same goes for fingerprinting. You try to identify models by their characteristics, but none of these go as granular as artifact level provenance, which is where you try to reproduce the actual output of the model, reproduce the model's weights and state at the time of inference at a later date. And that's what this paper provides. So I have a framework here. From left to right, we start with a deterministic inference layer. So this is where we set up the actual inference for the event, and that produces a provenance record. From there, you have a forensic logging system, which also adds information to the provenance record, including the hashes. You log the environment metadata. So I'll get into that further, what is actually being logged. And after that, I also include a reproducibility verifier, where at a later date, you can take the record that is generated and compare the hashes and make sure that everything was actually reproducible, that everything was verifiable, and more importantly, that everything was deterministic. So starting with the deterministic inference layer, there are 5 key things that are being done here. We start with enforcing floating point 32 precision. And this goes back to what I was talking about earlier with non-associative operations if you quantize the model. So you have to stay with the full model size. We also enforce greedy decoding, which is where you turn off temperature. That means that every single time the model will choose the same top word instead of k-random sampling or any variation of the matter. There's also global seed synchronization. So this is more for the environment, but you want to make sure you're using always the same Python, NumPy, and PyTorch libraries within the framework. There's also deterministic GPU configuration. So this means if you are using a GPU, which is more likely than not for running local models, all of this ties into local models as well. Cloud models are inherently just out of the picture because of what they represent. Local models are the only usable thing for this framework. We set the deterministic GPU configuration, so we force deterministic algorithms, not accelerated algorithms, for CUDNN and CUBLAS. We also have optimization exclusion, so there is no continuous batching, there's no prefix caching, and there's nothing similar to those things either. And that's for the actual inference, so when you make a statement, all of these are applied. After that, there's the forensic logging system that occurs after the inference event. So you have SHA-256 hashing. So this will hash the prompt, the model output, and most importantly, every single file in the model, in the local model weights. So that includes the configuration file, and it also includes the tokenizer. Because if anything ever changes on the server side or when you're pulling the model, this could be a factor for non-determinism. And everything up to this point shows that there are a multitude of non-deterministic things that can occur. So it's very important to capture all of this information, not just some of it. As far as the environment goes, the framework logs the OS, Python version, the GPU type, as well as versions for the core libraries, so transformers for the LLMs, PyTorch, and CUDA libraries. After that, we have the reproducibility verifier tool. And this happens at a later date past the inference time. So that forensic record needs to be stored somewhere securely. And once you have that stored, you can use this tool where you run a clean runtime reconstruction. So that means you're taking the entire forensic record, you're running a brand new subprocess. So there's no RAM saved, there's no caching of model weights, there's no cache. Then you perform bit for bit validation. So you rerun the inference. You compare the original hashes against the new hashed results, and you determine if there is any non-determinism. But based on the framework, it should be deterministic, and my experiments will show that later. There's also drift detection, which is just checking the environment, making sure it's exactly the same as it was in the past. And forensic reporting. This is the most useful part because it compiles all of this information into a more usable JSON file with a pass-fail message just to inform the user that the reproducibility passed. So getting into the experimentation, there are two experiments that I conducted for this paper. First, there was a system stress test and an adversarial robustness test, and I'll get more into what's actually happening there in a second. But for now, I want to explain that there are two distinct open weight model families I tested with, and that was the Llama model family and the Quen model family. As you guys can see, this is the specific models I used for the experiments. So getting into experiment one, we have the system stress test. So I took 10 unique prompts per model in each model family, and each prompt runs twice to account for per run or cross-model variance. This adds up to a total of 40 controlled inference and verification runs, and each time they're executed in a completely new runtime environment. And as you can see on the right, it passed every single time, implying that the first two phases of the determinism were enforced and they passed correctly. Next, we have the adversarial robustness test, which is where I conduct two tests within it to check for unauthorized tampering. So I append a single white space character to a prompt, which implies the identical semantic meaning, meaning that theoretically the model, if it has a temperature of 0, should reproduce the same thing. However, this framework is so granular that it would identify within the hashes that there is an additional white space character in the input, meaning that it is not exactly the same, making it not completely reproducible. However, because the system detects it, it is. For environmental tampering, I changed the set random seed to simulate invisible sources of non-determinism. And as we can see on the right side, this was also detected by the system. And this means there's a 100% flag rate across tampering and environmental drift. Moving on past experiments, we have the discussions and limitations. So one of the core things is system dependencies. This framework implies that you have to run the test and the reproducibility verifier on the exact same system. That's an open research area. So for now, I can explain a little bit more. I think I still have time. That GPUs, they run thousands of operations, and if they happen in different orders, there's a little bit of bit collision, and this implies non-determinism inherently. So this system must run on exactly one device. Another consideration is integrity over performance. So the framework intentionally excludes everything from high-through optimization, maximum VRAM usage because we're using floating point 32. And in practice, past this paper, I have ran this on a real system, and this is a real valid constraint of the system because the VRAM usage explodes incredibly with no quantization, as well as not a significant slowdown, but well, depending on the system, there is a reduction or an increase in latency. Future conclusions and directions for the paper. So this paper demonstrates that artifact level bit identical LLM reproducibility is achievable with limitations for local models. And it also provides a path for AI generated evidence to meet the Daubert standard, which in the future could mean that AI evidence could be admissible in court. As far as future work, I think analyzing latency and storage costs in order to scale this system even further would be the most important thing to make the framework more usable. Integrating it into existing digital forensic toolkits so that it's not a standalone system, as well as broader stability across different model families. That means more testing and diverse hardware environments, which would mean working on cross-system stability. That concludes my presentation. And if there are any questions, feel free to email me at the email on screen.
Yeah, so Joel, I have just one basic question. Like, since you have dealt with the large amount of data right over here, so during the data processing, did you face any sort of like issues, like whenever you were dealing with the test data and train data? Have you faced any sort of like challenges? Because you are writing your own LLM, right? For this specific
No, this is
scenario.
not for a custom LLM. So I ran these
Okay.
experiments. So the entire system applies for pre-existing LLMs. And the
Okay.
LLMs I used are Llama and Quinn.
Oh, Llama, right? Okay, okay. Then it's fine.
Yes.
Yeah. I was thinking like maybe means you are using your local LLM to handle the situation. Okay, then it's fine. Yeah.
Mhm. This would be applicable for custom local LLMs, though. The only constraint is that they must be local, not cloud-based.
Yeah, exactly. Yeah.
Mhm.
No, it is a good presentation. Thank you. Anyone
Thank you.
has any question, team, for Jewel?
I do. Thank you. I am quite curious if you think there is avenues for creating an abstraction layer to separate the hardware from the inference that you're doing in order to kind of take that variable out of the picture.
I don't think there would be any reasonable way to do that. This is just off the top of my head, of course. Um, because you would require a GPU to run any large local model. And if you're using a GPU, it's probably going to have CUDA, and that's going to be inherently intertwined with it. If there would be an abstraction layer, um, it would probably still have to be accounted for, at least to some extent, within the framework.
Okay, thank you. Do you see room for this like being run on large clustered systems that are self-hosted by digital forensics agencies? Like
I actually do.
Okay.
Yeah,
Larger
at my university, I'm
complexity,
currently,
great problem.
sorry, could you repeat that?
I just said larger, clustered systems creating more complexity is kind of where that leads me to think.
Yes. So the only issue with that is I'm currently working on something similar where this has been extended into an actual real system. Um, the complexity does increase. The only constraint is that everything needs to be run on the same system. So if you connect to a GPU, that specific cluster, if you want to use the verifier tool later on, you have to go connect to that same cluster once again. So there are workarounds for it, and the complexity does scale, but I do think it's still usable.
Awesome. Thank you. Great presentation.
Thank you.
Thank you. Yeah. So next, I'm looking for paper ID 50, Kindle, Strandridge, Asaf. Anyone of you is there? Okay. So then let me start my presentation then, because I have the next one. So let me share my screen. Yeah, can you see my screen? Okay. So yeah, means hi, my name is Sanjoy Mukherjee, and today I'll present uh, my research like titled an effective system for medical image diagnosis using deep convolutional networks, okay, in healthcare sector. Okay, so means from background perspective, like I'm working in the IT, but like in the life science as well as in the healthcare domain. So that's why like I was just kind of like looking for some sort of like uh, uh, if I can do something in this particular area. So that's why I've chosen this particular topic. Okay. So this work actually focuses on automated detection of diabetic retinopathy, a leading cause of preventable blindness. Okay. So here actually I am proposing a hybrid deep learning model combining CNN and XGBoost, okay, which significantly improve the diagnostic accuracy and efficiency. Okay. So yeah, means this slide is nothing but like what are the topics that I am going to discuss over here. Okay. So now let me give you some sort of like things that uh, like why I've chosen this particular paper. So as you know, like diabetic retinopathy or DEER, okay, is one of the most common complications of diabetes and can lead to irreversible blindness if not detected early. Okay. So manual screening is a time consuming and requires expert ophthalmologists, which is a challenging in many regions. Even right now I'm part of US. Even there are certain low cost region like where we are having this sort of issue. So in this work actually I use Mesidor 2 dataset, which is very common dataset and widely used like in the market, and they have some sort of like uh, image specific thing. So that I have chosen this particular data and applied the advanced pre-processing techniques such as clahe for contrast enhancement, Gaussian filtering for noise reduction, and image cropping and color normalization. I also apply data augmentation technique to improve generalization. I propose two models, that is Inception V3, a hybrid CNN XGBoost model. The hybrid model combines deep learning features extraction from CNN with classification power of XGBoost. And at this moment, like whatever I have done, and I'm going to show you like in the consecutive slides, like I have got almost like 99% accuracy, outperforming all other models. Okay. So next, I'm just reiterating some of the things like, as you know, that artificial intelligence has significantly improved medical image analysis, especially for modalities like MRI, CT, and retinal imaging. Okay. However, analyzing medical images is still complex and time intensive, right? So that is still those specific things are there. The diabetic retinopathy progresses silently and is characterized by micronephrosis and retinal damage. So early detection is critical but often missed due to lack of screening. So that's why like here means I am kind of like suggesting some sort of like AI based system which can reduce the diagnostic workload, improve consistency, enable early screening in remote areas. This motivates my work to build an accurate and efficient automated deer detection system. Okay. So now let me show you like what are the things that I have already gone through and wherever they have some sort of like lacking. So some studies have already been there right into this area related to deep learning of deer detection. Okay. For example, like as you can see, like ResNet 50 and DenseNet models achieve up to 98% accuracy in binary classification. And another thing is like traditional ML models like decision trees and SVMs show varying performance. However, many models either lack generalization or require high computational resources. So here my approach focus on combining the deep learning and gradient boosting to achieve both high accuracy and efficiency. Okay. So now I'm coming into the methodology, whatever I have used over here. Okay. So my system follows a kind of structural pipeline. Okay. First, I collect the Mesido 2 dataset for deer classification. Next, pre-processing is applied, means the Clahe improve constraints, Gaussian filtering removes noise, cropping focuses on relevant retinal regions, color normalization to ensure consistency. Okay. Then actually I applied the data augmentation techniques such as rotation, flipping, and brightness adjustment. The dataset is split into 80% training and 20% testing. Okay, that's a standard thing. Like I did not explore like, okay, if there is anything I can do over here. Then actually what I did, like I trained two models. Okay, one is the Inception V3, another one is the hybrid CNN XGV net. The hybrid model extracts feature using CNN and classifies them using XGBoost for improved decision making. Okay, so this is overall that methodology that actually I have used, and now I am coming into the result. Okay, so the results show, as you can see, that a strong performance improvement. The hybrid CNN exhibit model achieved accuracy 99.4%, okay, precision 99%, recall 99%, and F1 score is 99%. Compared to Inception V3, which achieved around 96.94% accuracy, the hybrid model performs significantly better. I know it is hard to compare, but at least like from both perspective, like hybrid CNN XGBnet is better. The accuracy and loss curves show stable convergence and minimal overfitting, indicating strong generalizations, as you can see over here. So then actually I did the further analysis like related to confusion matrix and ROC curves. The confusion matrix shows that the hybrid model correctly classified most normal and dear cases with very few errors. And the ROC curve demonstrated an AUC of 1.0, indicating near perfect classification capability. In comparison, Inception VT shows slightly lower performance. This confirms the robustness and reliability of the hybrid model. Okay. Now, actually, I did some sort of more analysis. Okay, just to make sure that yeah, whatever I'm thinking is correct or not. So I compared our model with several existing architectures like DenseNet 201, ResNet 50, VGG16, Random Forest, Decision Tree. While traditional and deep models shows moderate to good performance, the hybrid CNN XGBoost achieves the highest accuracy of 99.4%. This demonstrates that combining CNN with XGBoost provides better future utilization and classification accuracy. Okay. So now, what are the conclusion that I am coming over here? That diabetic retinopathy requires early and accurate decision. So that is obviously our hybrid CNN XGBnet model significantly improves diagnostic accuracy. The model achieved 99.4% accuracy, outperforming existing approaches. And this approach has strong potential for AI assisted screening systems deployment in low resource setting. That is one of the things that even I have started talking with some of the NGOs in US, like to make sure that if they are interested to acquire this specific model or not. And another approach should be like the large scale automated diagnosis. So yeah, definitely there are some future work required, okay, which includes like multi-disease retinal analysis, because right now I'm just concentrating only one specific uh, area like the diabetic retinopathy, but in later point of time we can explore like into those area. Then the clinical validation and the integration with the real-time healthcare system, like if there is any sort of like patient service application like which can be integrated with those sort of like model. Okay, so yeah, means that's all like so far, and I'm not going to discuss these references. Okay, but if you have any question, like I'm definitely reachable. Yeah, I forgot to mention my email address over here, but yeah, my email address is sanjoyp158@gmail.com. So yeah, thank you for listening me. Anyone have any questions related to this topic? Okay, thank you. Thank you for listening.
Are you able to listening? Can you hear me?
Okay, let me. check one more time. Paper ID 50. Did you guys join? Kendall, Standridge, Asaf. Okay. Then I'm going to paper ID 146. Okay. Janvi. Okay.
Hey Sanjeev, can we drop, right?
Yeah. We can drop anytime. Yeah.
Okay,
No need to
thank
stay.
you, team.
Yeah. Means if you
Okay,
have any other work, you can drop. Not an issue.
okay,
Yeah.
okay, thank you. Bye.
Yeah.
Hi, Sanjeev.
So Janvi, are you there? Paper ID 146.
Yes.
Okay.
Hello. Hello.
Your voice is pretty low, Janvi. I don't know it is for me only or not, but it's pretty low. Your
Are you
voice.
able to hear me?
Yeah, now it's clear. Yeah.
Yes. Yeah, I was trying. Let me share my screen. And yes.
Yeah.
Okay. Thank you so much, Sanjoy, for leading this session smooth and nice. I really enjoyed your conversation because I think there is some
Oh, it
synergy.
is almost similar to my topic, but in the other
Exactly. Yeah.
side of the
Yes.
things. Yeah. But
Yeah.
it's good. Yeah. Let's
Uh-huh.
see.
And also ISDF for providing this munch. My name is Janvi. Today I'll be presenting. Let me try to minimize this. Okay. So I'll be presenting enhancing early diabetes screening through machine learning and explainable AI. What we are suffering from is like we know there are worldwide diabetic patient, but how to detect those diabetes system early and even their early signs of diabetes so that we can intervene and resolve the issue. There are some AI solutions, but the question is how reliable and how accurate those systems are. So I will start by discussing what is current situation that we are trying to solve, then going over some comparison between the existing solution and how my methodology is different. Going through the architectural diagram by talking how I collected the data and how did I evaluate the system, and then I will touch base on results and discussion, following by conclusion and future work. Here, I'll discuss what are some of the things we still can improve to make this system more adaptable and deploy in real world use case. Now, early diabetes detection is why it's essential and crucial, right? So if we do not intervene early, or if there is no early detection sign of it, then it causes metabolic challenges, which is like significant. And I'll also talk what kind of issue that might occur if we detect or if we make a little bit delay in detecting those. Study explores that ML models with explainable AI can help clinicians to detect very early stage. And today I'll be utilizing PIMA Indian diabetes dataset. I'll be utilizing a hybrid ensemble model, which is like combination of catboast, random forest, decision tree, and at the end, soft voting, all those models. And will be evaluating against F1 scores, reliable metrics such as, we can't go with accuracy because we want to emphasize more on precision and recall, and we want to get higher numbers on both those metrics. So we'll select the models based on F1 score. And as I told, explainability is crucial. So I will be using SHAP and LIME method to make it more interpretable rather than having just one black magic box. Today, in the worldwide, there are 589 million peoples, which was, if we go by numbers and very documented numbers, in 2021, we observed 537 million people, but nowadays that number has increased and it's like 589 million people, which is 11% of young population. And that is huge. Now, traditionally, diagnostic method detect diabetes, but if we do not detect on time, the patient might suffer from cardiovascular disease or neuropathy or kidney damage, which are very critical long-term disease. And the diabetes mainly divides in type 1 and type 2. Today method will help us to detect both the types. And as I told, I'll be utilizing multiple models to come up with one standalone solution. To understand what other people have done in this area. So I have, pointed or selected few comparative analysis of one, which was conducted in 2023 on PIMA Indian diabetes. The other one is combination of few data sets. Then there is few more on the different data sets as well. And all these models that they have used, some of are mainly machine learning models, some of their even deep neural network. And we see the best performance, which is, I would say, 98% accuracy. But in all this research paper, one thing which is, lacking is explainable AI. How does this model outperform? And how do we trust on this model? So that's what the gap area which I'm trying to emphasize or targeting on. This is my method. I have collected data set, which is PIMA Indian diabetes. Then I applied some data pre-processing, is basically removing some outlier with interquartile range. Then applying normalization, we also have multiple methods for data pre-processing, such as standardization, dealing with imbalanced data. So since very few percentage have diabetes, which means there was highly imbalanced data, so I used MOT method to make it balanced data and then split the data, use ML model, and then after that use explainable model, and then collected the results. Result and discussion. So what we can see, it doesn't have a solid accuracy, but at the same time, I try to focus more on getting precision and recall at the same time. So that's where the F1 score stands at 97%. Our goal is not to wrongly identify the patient without having diabetes as a diabetic, and the patient who have diabetes or suffering from diabetes, and we mark them, they are regular patient. So we wanted to focus more on both those age cases, and that's why I collected F1 score, and we see the system is fairly reliable. Here, I have plotted 3 graphs, which is like ROC curve, which again emphasize on precision and recall. Then there is a SHAP, which focuses more on global, which variable are highly valuable or, decision breaker. We can see the features such as glucose or age or BMI. Those are very, important feature that is predicting the end result. And then there is a line plot which can tell us per feature what is the outcome, per row which feature is driving that result. Now, a result in comparing to only the people that have used PIMA dataset, the dataset that we have used. And by the way, this is very popular data in Kaggle. And what we can observe here is the other people have used AdaBoost, Random Forest, ResNet 18, but my approach, which is a combination of few models, which leads me to higher accuracy and higher F1 score. Conclusion and future adaptability that I can think of is diabetes is a serious metabolic disorder and which require accurate and early detection. Because of this, and there is a huge gap in number of people that need cares and clinicians nowadays in the society. Because of that huge gap, if we can use AI to detect this severe diseases very early in the lifespan, that can help our patient to give good care, good support, and they can live their life longer. So here I try to use very efficient evaluation methodology, efficient machine learning algorithm by comparing several approaches, and then using this to make it more interpretable and reliable for clinicians so that they can actually use this system, and this system is can be deployed in real environment. These are the references that I have used, and thank you so much, everyone. I really enjoyed presenting this to you. I'm open for any question. And I also have dropped my email ID if you would like to reach me in later stage.
No, this is good, Janvi. So one thing I'd like to know this Pima Indian database, like so whenever you are loading the records right into your model, okay. So is there any specific technique that you have used for loading the records into the LLM, or how did you load the information? Like any
Yes, so
specific mapping mechanism you have used over there?
mhm. I completely understand why you are concerned around that, because the data set is huge in size, and sometimes if we load it in our local system, the system might hang. So I use Kaggle notebook to run it against GPUs, where I divided the whole data in batches. And since I use mode, which is like upscaling the data of minority class, first I applied SMOT and then divide the data in balance batch, where the patient having diabetes versus not diabetes is balanced in all the batch, and then pass it to make a prediction against the model.
Perfect. Okay. Yeah. Does anyone have any questions for Janvi? Okay. I think we are good. Thanks, Janvi, for the presentation. It was
Thank
nice
you.
presentation. Yeah.
And if you can drop your LinkedIn, I would like to connect everybody in this
Yeah,
conference.
definitely. Sure. Yeah. So next is yeah, so I'm just asking one more time, paper ID 50, Kendall, Strandrich, Asaf. Have you guys joined? Okay. Next, I'll go for paper ID 148, Maunik K. Shah and Munir Rajesh Mehta. Are you guys there?
Yep,
Okay.
I'm
Yeah.
here. Can you hear me?
Yeah, we can hear.
Is my screen visible?
Yeah. I can see.
You can see. Okay, cool. Hello everyone. So I'm going to talk about my paper on privacy preserving healthcare using federated learning with differential privacy mechanisms. The uh, the premise of the paper is that the raw data of patients and the healthcare records are generally distributed across the different hospital institutions, and aggregation of such sensitive patient information to train models exposes the data to cyber attacks, inference attacks, third-party access, non-compliance with laws, because the obviously the patient record EHR laws around are very strict with GDPR and HIPAA. So it is hard to collect all the raw data and train a model that can be used to accurately be useful. So in this paper, we are looking at the possibility that instead of gathering data at a centralized location, can we train local models at institute level and share the model data at the centralized location to create a larger model using something like a federated average model that can be accurately be able to be practically be used to make the decisions that are required to be made. Funnily enough, I also choose an example of diabetes, specifically the readmissions due to diabetes data. This data set one of the reasons why I went with this data is because the data related to this from 130 hospitals are already available in Kaggle, and as you have seen, there has been a lot of other studies done on this problem as well, which gives us more data point to compare our results against from. So in this paper, I use the deep neural network, aka DNN model, for centralized learning, and then a federated learning with a federated averaging algorithm to average this local weights into a single global model. And third thing that I basically did is also basically add the differential privacy by introducing the gradient clipping and the Gaussian noise addition on the federated learning model. And we will compare the accuracy, Affine score, precision recall for all of those three approaches, and then we'll also compare results against the classical models like random forest, KNN, SPM, logical regression, etc., etc. So here is the primary literature review that basically not only just motivated our study, but also give us the insights on what the baseline we should be. And here is the a diagram mentioning our overall high-level methodology. I'll talk about this slide because this is slightly more simplified in my opinion. So again, we are taking the diabetes 130 US hospital data set collected from 1999 to 2008. This data, as you can understand, is collected from 138 different hospitals in this research, and our methodology begins with a robust dataset cleaning. Dataset is consisting of like over 50 clinical and demographic attribute covering multiple years. So during our exploratory data analysis, we did see some imbalance between the patient population diversity, and so we did basically also noted significantly racial disparity as well. So we use the pre-processing stage to exclusively balance those data. This involved also dropping the data with features that are missing values, such as sometimes the weight and some of the lab results were missing. This all basically reduces the different dimensionality and the noise. And then we applied the label encoding to categorical features and transformed the red-muted variable into a binary format for classification. The critical step in our pipeline was obviously to address the class imbalance. The raw data was heavily skewed, with only about 11,000 readmission cases compared to nearly 89,000 non-readmissions. So we employed the SMOT to synthetically balance these classes, ensuring our models weren't just biased towards the majority. After standardizing feature using a standard scaler and splitting the data into the 80-20 training and test data set, we are ready to implement our models. So we specifically chose, again, as I said, three different approaches. One is the centralized DNN to set our performance ceiling. Essentially, obviously, the premise over here is that as you go towards federated learning, the accuracy and accuracy would drop, but we want to just see that how much accuracy drops, and even after dropping that accuracy, it is still usable in the real setting or not. So centralize a DNN to set the performance ceiling, and then we used the federated learning without any differential privacy mechanisms, and then obviously using the federated average algorithm for the data locality, and finally, we use the federated learning model with differential privacy to provide the mathematical guarantees for patient confidentiality. And each of these were rigorously measured using a suite of metrics, including accuracy, F1 score, and precision recall, and everything. So moving on to the results analysis, the performance of our models clearly illustrates that the expected trade-off between absolute accuracy and data privacy. So our centralized DNN achieved the highest performance across all metrics, reaching a peak accuracy of 86.81% and F1 score of 86% again. And as we transition into the distributed or federated environment, our federated learning model without privacy maintained a strong accuracy of 84%, when we introduce the differential privacy mechanism to secure the patient data, we observe that the competitive accuracy is basically dropping to 83%. So as you can see, there is a trade-off analysis. The privacy cost, as we can say, for the accuracy or the performance drop attributed to the addition of the differential privacy noise was relatively small at only 1.45% when you compare federated learning with privacy and without privacy, and close to 3.5% when you compare centralized learning to the federated learning with privacy preserving mechanisms. So this indicates that our platform is efficient at preserving utility while enforcing strict security for the data. And looking at the confusion metrics again, for our top performing model, we see a balanced ability to correctly classify both readmission and non-readmission cases, which is vital for the clinical intervention. So the most significant takeaway over here from this slide I want people to take is the slight performance decrease inherent to the privacy preserving federated setup. The model still remains accurate enough for real world healthcare applications, and it successfully bridges the gap between the need for high precision predictive modeling and the stringent regulatory requirement for handling the sensitive medical data. And to truly understand the value of our proposed framework, we compare it against the classical machine learning models traditionally used in healthcare analytics a few years ago at least. And as you can see in table 2, our centralized DNN serves as a performance ceiling at peak 86.81%, which makes sense. Because of the amount of parameters and features that the dataset has, the complexity of the data, and the DNN can extract more signals out of those data than classical models like random forest or logical regression. So that doesn't surprise. That is not surprising. However, the real breakthrough is visible when we compare it against our privacy-preserving models. So even after accounting for the privacy cost of the distributed training and differential privacy noises, our federated model with differential privacy achieved an accuracy of 83%, which is particularly significant because it outperformed all classical baselines, including the highest scoring model random forest, which trailed at 82% accuracy. The other methods like logical regression, KNN, SVM fell significantly further behind in this case. So the key takeaway of this slide is you don't have to choose between high performance and high accuracy. While centralized deep learning technically offers the best raw results, our privacy-saving federated learning represents the most effective trade-off. It provides superior predictive power compared to traditional model while remaining fully compliant with the security and regulatory requirements of the modern healthcare system. So to conclude, the clinical importance of accurately predicting hospital readmissions cannot be overstated. By identifying at-risk patients early, we can significantly enhance patient outcomes, decrease the financial burden on the healthcare system as well. And in this paper, we successfully provides a privacy-sensitive framework that integrates a federated learning effectively with the differential privacy to meet these needs. And again, our centralized deep learning always will be setting the benchmark, but our federated approach proves that we can achieve highly competitive results without revealing the raw patient data or making them a target of inference attacks. Our trade-off analysis shows that it is marginal, 1.45% compared to other federated learning, and 3.5% compared to the centralized deep learning, and with applying the privacy noise, of course. So making this framework incredibly practical for real world and other privacy sensitive applications. So and looking ahead, we acknowledge certain limitations such as communication overhead, the need for testing on multimodal data. So the future scope involves investigating the non-IID and cross-institutional environment, as well as adapting differential privacy mechanisms to improve scalability. Overall, this finding indicates that a combination of federated learning and differential privacy is a powerful direction for achieving safe and regulation compliant environment in the modern healthcare. And just listening to other papers today, I think this is also the one of the more feature scope, the combination of models that you guys are using for diabetes accuracy prediction. Maybe that is something we can also apply into the federated learning setup and see how what kind of higher accuracy we can achieve compared to, especially compared to the centralized DNN model in this thing. So that's it from me. Thank you. Here are the references that I used, and that's it from me. Thank you. I'm open to taking any questions.
Yeah, no, I think this is good, Monique. Yeah. Yeah, means whatever you were telling means I think some of the things maybe we can coordinate and something like we can build, like whatever the data that I am processing, maybe I can mark it through your process and then we can determine, yeah, how the things are working. Yeah.
Absolutely.
No, this is good. Anyone has any question? No, I think, yeah. Thanks, Monique. It was a nice
Thank you.
presentation. Thank you.
Thank you, Sanjay. Thank you, Sanjay.
Okay, next one is. Okay, next one is Sean. Your paper.
Yeah, let
Paper
me just get my
270.
screen shares set up. Can everybody hear me?
Yeah, we can hear you, Sean. Yeah.
Okay. How's that? Screen's up?
Yeah.
Okay,
Yeah.
great.
Yeah.
Okay, so good afternoon. Thank you for being here. My name is Sean Alderman. I'm presenting our work conducted with my co-author, Dr. John Hastings of Dakota State University, on unsupervised baseline clustering and incremental adaptation for IoT device traffic profiling. Our research explores unsupervised clustering, novelty detection, IoT device fingerprinting, incremental learning, and lightweight network flow features. In the next 10 minutes, I'll walk you through the problem, our approach, the results, and practical insights. IoT networks are incredibly dynamic, heterogeneous, and device behavior is constantly evolving. Devices join, they leave, firmware updates happen, changes in behaviors due to legitimate new features or device compromises all lead to a very unpredictable environment. That combination creates a lot of real headaches for defenders and investigators. Static models tend to degrade quickly, often losing up to 40% accuracy from concept drift. So what is needed is something that is packet efficient, fully unsupervised profiling that adapts over time without starting from scratch. Our goal is true device discovery with novelty recognition. So that's something that's new traffic is not always novel. It may be the first time we've seen it, but it's not something that's brand new, completely unseen. So most prior work falls into one of two camps, either heavy supervised training on labeled data that produces these static profiles, or purely adaptive online learning that never quite builds a solid baseline. Real world deployments need kind of both at the same time, robust fingerprinting plus efficient updates for behavioral drift and the introduction of new devices. Long-term realistic traffic capture is also essential. This paper fills that gap by using the Deakin University IoT traffic data set and a fully unsupervised incremental pipeline. So our two research questions are: how well do packet efficient feature flows actually enable high quality unsupervised IoT device profiling, measuring cluster quality and noise rate? And once those features are engineered, how effectively can an incremental unsupervised profiler adapt to new devices while still retaining performance on known devices and keeping the update cost low? Our contributions are pretty straightforward here. We prove the viability of our flow features plus unsupervised clustering with dbScan. And we demonstrate practical incremental adaptation using the exact same features with Birch. And we quantify every trade-off on real data over long time periods. The pipeline is clean and modular. We perform feature engineering that is reused in both stages. Stage 1 builds this strong baseline profile using unsupervised clustering. Stage 2 then proceeds to incrementally adaptation of those profiles as novel devices appear in the data stream. The two guiding principles are keeping everything practical. We want to stay efficient from a packet perspective, and we want to completely avoid any dependence on large labeled data sets. This design makes the work immediately usable for real-world operations. We evaluate the Deakin University IoT dataset. Note the dataset comprises 24 labeled IoT devices, additional non-IoT background graphic, and it's taken from over 6 months of device operation behavior. That gives us a long-term coverage across every phase of the device life cycles and realistic background noise. We also structure the evaluation around varying levels of device novelty. This setup is a much stronger configuration than the simple test train split concept. To test true novelty handling, we create the idea of 3 novelty categories. Low novelty is like different devices, but same make, model, and purpose. Medium novelty is kind of a mash between similar function devices, but from different manufacturers versus different same manufacturer, but different functions. And high novelty devices, which are completely unseen, brand new to the network, and we don't understand its model, make, or purpose. We select high novelty device as an AOTech smart hub, and out of a low novelty device as one of the Withings body plus scales in the dataset. To begin, we merged 3 training PCAP files that deliberately exclude the hub and the scale, and then tested on an unseen PCAP file that contains all the devices. This novelty-aware split gives us a far more realistic evaluation than those standard test train split methods. We extract bidirectional feature flows from the raw PCAP files. No payload inspection, becomes very data efficient. The models use exactly 25 numerical features split into 2 groups. Static identity features come from things like MAC address values, TTL modes, various different other network ports and protocols that the devices use. And then we create dynamic behavioral features such as inter-arrival time statistics, packet rates, and sizes, protocol ratios over various different time windows. Temporary identifiers like DHCP host names that may indicate device data are included but excluded from the modeling. We just use those for debugging purposes to make sure we know what we're looking at. And all features are reused and unchanged in both the baseline and incremental stages. For evaluation, we combine both internal and external clustering metrics. This gives us a robust evaluation. Normalized mutual information measures alignment with ground truth labels, while Silhouette evaluates cohesion and separation of clusters without needing labels. The incremental adaptation efforts in research question 2, we introduced 2 new metrics specific to the novel devices: purity, how clean the new device clusters are, and share, how much of the novel devices traffic is captured by the cluster. We also track known device accuracy after each update and the raw computational cost in every cluster for update time. To begin, we use we baseline benchmark for 4 classic unsupervised models: K-means, dbScan, HDBScan, and Birch. dbScan delivers the best balance with the best NMI score and a very respectable and high Silhouette score. HDBScan is close second. Both K-means and Birch do not perform very well in this. They have extremely high Silhouettes, but the NMI scores are very, very low and unusable.